Hello students, here's a practice exam problem set for exam 2. This problem set is written for practice exam, not for actual exam problem set. So this covers a little bit more than usual and a little bit more intensive than the actual exam would have been. Please keep that in your mind. And let's go. First category, some antiderivative computation problems. There are so many fractions, so it's going to be better if I increase the font a little bit. Okay, here we go. Here we have some straightforward power functions and some fractions. Here's a problem that requires some power form conversion. And here are some exponential functions. And finally, here's the problems with trigonometry. Okay, let's go to the first problem. X to the e power, that's power function, straightforward. E to the x power, again, that's a power function, straightforward. E to the e power, what kind of function is it? Actually, this is a constant. Now, x to the e power, what kind of function is it? And finally, e to the x power, what kind of function is it? First three are pretty much straightforward. Power function, exponential function, and then that could be a bit tricky, but by this time, everybody can clearly see it, I hope. It's a constant. Now this one, this fraction is actually a power function too. And this one, the hardest of the bunch, that too is a power function. Turns out, x to the e power is nothing more than 1 over e times x, or x to the first power. And more importantly, e to the x power is actually e times x to the negative first power. They're both power functions. So, power function, exponential, and then constant, power function, another power function. So, x to the e power, it'll become like this. Just use the power rule, add the power by 1, and then divide. Exponential remain the same. Wait a minute. Okay. Okay. I have to add 1 to the power and divide. 1, so I don't have to add it, and then divide. Dividing by 1, I don't have to do it. Okay. Quick correction. And then this one, add 1 to the power and divide. So second power and then divide by 2. And finally, negative first power, that's going to become a log function. So here, this red part became that, and this blue part became that, and then this green part became that. Okay, there goes the solution. Next, this problem can be done through substitution, but it's going to be an overkilling. It's going to be a lot easier if you convert it directly into a power form of negative 2/5 power. Do you see it? Denominator, so it's negative power, and then second power, so that's numerator, and then fifth radical, so that's a denominator. So we got that. So add 1 to the power and divide. So that's how you get 5/3, the reciprocal of 3/5. And then finally what? We have this coefficient 3 that goes to the denominator. Yes, you can do it through substitution, integration by substitution, but that's going to be a bit of an overkilling. If you do it right, after a lot of difficult process, you're going to get 1/3 anyway. You can regard it as just undoing the chain rule. If you take the derivative from here, this 3/5 will be multiplied up front and then cancel each other out with this coefficient, and then subtract 1 from this power, eventually leading to negative 2/5 power. But by chain rule, you have to multiply the derivative of the inside. That's 3, and that'll cancel each other out with this 1/3. So that's why we are having this 1/3. If this had been some other, say 4, then this had been 1/4, and so on and so forth. Okay, here's the next problem. We have a bunch of exponentials. How do we handle it? Well, as we discussed previously here, there's no such thing as quotient rule in antiderivative computation. So somehow you'll have to express all those into simple power form or simple exponential form. How do we do that? Well, here's one way to handle it. Denominator is just monomial, just one exponential. So separate the numerator like this. And then separate the numerator, as you see in the right hand side. And then like this, you can simplify each exponential. Simply subtract the power w plus 4 minus the power 3w plus 2. Just subtract. W minus 3w, negative 2w, 4 minus 2, so plus 4 like that. And then again, we just subtract. Subtract. And then next is easy. Exponential always remain the same, but divide by this coefficient. Again, the idea is undoing the chain rule. Divide by this, so undoing the chain rule. And finally, this looks like exponential function, but there's no w there, so it's just a constant. So you just gain w because this is constant times w. And then there'll be a simplification, which is not really necessary. That's one way to handle it, separating the numerator, and I usually do it this way. Some students prefer to do it this way though. Change the division into multiplication. And be careful here. Some students do it as 2 times that, just changes the entire denominator to multiplication. No, it doesn't work like that. Number parts stay down below, and then the exponential part, we have to take the negative so that you can flip it over to the numerator. And then we do multiplication. So basically we are adding up the power. This negative 3w minus 2 plus w plus 4. We're adding up. Negative 3w minus 2 plus negative 2w plus 5, adding up. And so on. And of course, as before, you're going to get this expression. Same as before. And take the antiderivative term by term. Exponential stay the same. Undo the chain rule. Exponential stay the same. Undo the chain rule. Exponential stay the same. Oh no, this is not an exponential, just a constant. So we just gain w. Okay. All right. Now, trigonometric functions. How do you deal with those? Antiderivative of sine is cosine. Antiderivative of cosine is sine. Actually, antiderivative of sine is negative cosine, excuse me. Those will help as a matter of fact, because we have the sine of theta showing up here, and that antiderivative is negative cosine, and then we have cosine there. So how does it work? Takes a substitution, u as 5 minus 2 cosine of theta inside of a composite function, and take the derivative, and then solve for d theta. Do you follow this computation? And then let's substitute everything back in. This d theta is substituted to this d theta, so that we have 1 over 2 sine of theta times du, as highlighted in red. And this u, 5 minus 2 cosine of theta, go in place of 5 minus 2 cosine of theta and becomes u like that. And then go ahead and simplify a little bit. Looks like sine of theta cancel each other out, and you just get a u integral. If you have extra theta term here, then you will have to go back to this substitution and then work something more. But in this case, you didn't have to do that. Turns out it is a power function. As a matter of fact, here a lot of students make mistake of taking the logarithm. That's why I'm emphasizing the power form. instead of going directly from 1 over x to log, changes to actually negative first power and then going to log. That way you can cut down some unnecessary mistakes. From here, instead of going directly to logarithm because it's the denominator, changes to power form, u to the negative 1/2, then you can clearly see, oh, this is the usual power function. It's not going to become a log function. Add 1 and divide by this power. We get, well, after this cancellation, we have 1/2 power. And substituting 5 minus 2 cosine of theta back into the original, we get this expression. You can change this 1/2 power form into square root if you prefer. Personally, I prefer the power form. Okay, so much for the antiderivative computation problem. Next, let's go to area problems regarding this kind of curve. And then, well, isn't that this function that we just discussed previously? Yes, the very same function, except that we have character x instead of theta. So we can use exactly the same computation as before. But then again, how do we use the antiderivative of this? Well, we have an area, so why don't we simply take the antiderivative and then take the definite integral from negative pi to pi? That's not going to work because we have plus part and minus part, which will cancel each other out. Remember, definite integral is signed area, not the geometrical area. So just adding up will not do. How do we make it right? Take the area of this part and then double it. You see, you have symmetry, so it'll work out. So the integral from 0 to pi and then double it. Now as for calculating this integral, we already did it in previous problem, so let's recycle that computation. We already did it. 5 minus 2 cosine of x to 1/2 power, or equivalently square root of that. And then plug in pi and plug in 0, subtract one from the other. And cosine of pi is negative 1, so as a matter of fact, 5 minus of negative 2, so we have plus, so square root of 7. Cosine of 0 is 1, so we have 5 minus 2, so square root of 3. And there you go. That is the precise area. Oh, we have to double it. This area, and then we have to double it. So here we go. 2 times square root of 7 minus square root of 3. Okay, expressing the area as an integral is probably half the problem. Just 5 points only, not entire 10 point. Now let's discuss section 3 graph problems in a separate video. See you soon.